Hi there, my name's Nigel Griffiths. I work in Power Systems Advanced Technology in Europe. In this movie we'll be looking at some frequently asked questions in the area of POWER7 Performance, Entitlement, VP, Affinity and Memory. I get asked lots of questions, usually via email, every week, and I've sort of taken a lot of those together and made up some questions which are fairly typical. For every person that asks me a question, there's probably another 10 people out there that have the question but never really find an answer. So I hope this helps. So the first question then from Jim. His virtual machine has an entitlement of 8, virtual processor count of 10, SMT4, so it must be POWER7 or 7 Plus. And he asks why with only 20 users out of twice as many possible, is he already using 9 physical CPU cores? I guess the subtext is if more users log in, he's already at 90% of his physical cores used, and he may not be able to cope. Well, Jim, I like your question, and I like your LPAR configuration too. You've got an entitlement of 8, and the VP number is just a bit higher to give yourself a better contingency. But, as you set the VP to 10, you have stated that you're happy with this virtual machine to use 10 whole CPUs. And the default behavior of AIX is to use all 10 virtual processors for maximum performance. That's what most people would actually want. If the VP is 10 and the workload grows, it will quickly grow to use all 10 CPUs. But it'll only be using that first SMT thread on each of those 10 cores. And it will do that for maximum performance. Then if you've got more workload, more processors that are runnable, then it will start allocating work to the second SMT thread, and then the same again for the third and fourth SMT threads that come in together. So with just 10 busy processes, maybe each user brings a busy process with them, or if you have 20 processes using half a CPU each, or 30 processes using a third of a CPU each, you get the idea, then you will find you'll be using all 10 virtual processors, or 10 CPU cores when they're actually running on the processor on the hardware. Those 10 CPU cores will be 100% allocated to this logical partition. Well, 8 of them are guaranteed because you've set the entitlement up at that. The other 2 will depend on whether there are spare CPU cycles available in the pool. So you've asked for 10 virtual processors and you'll probably get 10 virtual CPUs. This is what you've asked for, even though you don't need to run the extra SMT threads. So what's the effect of those SMT threads? Well, you can still allocate more processors to them and get more work done. Of course, they are not more cores, they are time sharing, cooperating and using those instruction units inside the same core. And for a sort of ballpark placed of how much extra work you can get done, 40 to 60%. Very, very difficult to predict. It depends on the application instruction streams inside those processors. And there's no real way of diagnosing those apart from running it and seeing what happens. Well, can we actually see this on the machine? Well, yes we can, and we'll do that in a second. Quick reminder then, and SMT threads are reported by the tools as logical CPUs. The virtual processor is mapped to a physical CPU core when it's actually running. And if we have SMT4 switched on, then one virtual processor will show up as 4 logical CPUs. Don't forget, with our intelligent SMT threads, as we have with POWER7 and 7 Plus, we can dynamically switch SMT mode. Although the official mode is 4, running 4 logical CPUs, if it hasn't got enough processors to actually run, it will dynamically switch it to 2 or to 1 because it's more efficient to run it that way. We can actually see that in the numbers for some of the commands. So here we are on my wiki server called Blue, and we'll look quickly at LPAR stat-I. So we can see it's a shared processor, SMT4. We're uncapped. The entitlement is 2, so it's different to Jim's configuration, but we should be able to make a few points in here. And the VP is currently 4, so we have SMT4 and VP4. Don't think anything else is particularly interesting in down here. We have active memory expansion switched on, and we actually have the dynamic power saving switched on, favour performance, so we can do some overclocking if we get very busy. Well, we ignore those for the rest of this demo. Let's switch on then the best performance tool in the world. Here we go. And we'll just click on the CPU. Not much happening on my web server, some little things ticking over as people look at my website. I think a lot of people are on holiday today. And I want to run a program that will generate some workload. I'm asking it to run 3 processes flat out in the background now. We'll have another look at nmon, and we can see here very quickly we have, remember those details, VP is 4, that's down in here, the entitlement is 2 up in here, and most of the time we can see we have those 3 running programs sitting here, here and here. Now it hasn't used the first CPU because this is actually running my web server. It's coming in now and again, just little amounts, so it's decided to actually run these 3 hungry CPU programs on these particular cores. We have SMT4, so if we look at CPU 0 to 3, this is one virtual processor. It maps onto a physical CPU core while it's running, and SMT4 generates these 4 logical CPUs, and we can see we're not actually not doing much. If we take an example down here of the last one, here we have the last VP, the 4 logical CPUs, the SMT threads, and it's running almost entirely on that first thread, user 100%. Interestingly, just these 3 programs, occasionally my web server doing something on top, our entitled capacity in here is 150% because we're using 3 cores out of that entitlement of 2. We're also using 75% of our virtual processor. We have 3 out of the 4. Okay, this is very easy to understand that we're only using these first threads, the first SMT threads in each of our physical CPU cores. Let's clear the screen, and we'll now try a regular mpstat, an AOX command, and we'll get it to output this once every 2 seconds. I'll actually just Control-C it there to save it moving around while we're talking about what it's actually doing. Again, we can see, take the last one in here. We'll ignore the all, which is a summary of the whole LPAR in here. So 12, 13, 14 and 15 logical CPUs are the SMT on the last virtual processor CPU core. In here we can see this minus sign in here, which is telling us that this SMT thread is effectively switched off. This is the intelligent threading, switching them off because we've only got one process to run, and it's better to run that on one logical core all by itself, not competing for resources. mpstat is trying to show that although it's 100% user time, we're only using 63% of the potential physical consumed. If we had more SMT threads, we could get the other 37%. We can see this then, this is 63%, 63%, 63%, 63%, giving you a feeling of how much more work could actually be done on this particular machine. The first physical core up in here is running my web server. It's running it 25% and system time up in here. Oh no, it's not actually. It's got 25 and 58% utilization in here, but it was only actually running on the physical consumed core in here of 1% of the time. So when it was running 1% of the time, the mix of system and user time was 58 to 25%. System time, of course, is what's normally system calls, a program asking for something to be done, or interrupts happening. And this is probably, because it's so low, the interrupts actually happening for the disks and the networks, and the clock interrupts actually happening. So this actual core was only 1% used. So this is actually free in this particular configuration. Now we can get this similar sorts of data in Topaz actually. If we start that up, we look like this, and I'll hit capital L for logical CPU stats. Give it a second to catch up. Here we go. Again, we've got the CPUs down in here, and if we look at that last virtual processor, the CPU core, we can see the same numbers as MPstat was reporting in here. 63, 63s, and it's got a little blip has come up, and it's back down to the 1% usage. Well, hopefully that's given us a feeling for how much extra this LPAR could actually deliver if we got busier and if we had enough processes, or it could be multi-threaded programs, actual process threads, to actually keep all these SMT threads busy. So Jim, this is the expected behavior. It will spread out, maximize the resources that you've given it. So you need to check your spare capacity on your logical partition. I suspect you will have the resources needed for your other users. The next email is from Jane. Typical scenario, a Power 770, so a reasonable sized machine, 85% busy, so they're actually making a lot of use of their machine. They have a vital LPAR with a setting of entitlement 0.4 and VP4. I see this quite a lot on a lot of machines. Same as a Power 6 machine, but they said now the performance is slow, the applications seem to hang, the users are revolting. Well, it's an old joke, isn't it? But the users are revolting, let's face it. They're probably also complaining if the system or the application is hanging. Now, I don't like this particular configuration of entitlement and VP numbers, and I can explain why. We'll have some diagrams later on, but let's have a look at this particular one. I actually say this is like my son's just passed his driving test, and he's going to drive my car, and I say, well, I think he could stay below 40 miles an hour while he's still learning. And so I set the governor in my car so that it can't actually go more than 400 miles an hour, so that you can safely overtake. And to quote Homer Simpson, dope! It's obvious that that's a pretty dumb way of setting up my car. He doesn't need that amount of safety margin. In this case, it's exactly what we got, haven't we? Here we've got 0.4 and 10 times that. If you imagine this was 40 miles an hour, this is 400 miles an hour. Maybe it's just the low numbers in here that gives us a false sense of what's going on. We guarantee in the entitlement 0.4 of a CPU, but we're happy for them to use 10 times that. Now, there's some implications in here that a lot of people aren't aware of, the virtual processor numbers. Let's have a look at that. So when we actually start up this virtual machine, entitlement 0.4, so the hypervisor says, okay, this is normal usage. I'll allocate that much CPU power to a particular core when it starts up. And so it's selected this core down in here. It's running a couple of other LPARs in here, so it's fitting them all together as it's a fairly busy machine. And you're allocated 0.4. It then makes a note that your VP is 4, but it doesn't know where it will be running those at the time. We'll have to work that out later on. It also says, okay, the memory for this logical partition, as this is our home CPU, then we'll allocate the memory there, and they've got nice local memory for our entitlement worth of CPU. Now, as we start up more processes here, we use more than 0.4 of a cores. And let's say the other LPARs on this processor are busy too, and so the hypervisor realizes that to get more CPU cycles it has to use other CPUs. It will try and find one on the same POWER7 chip, because that will have local memory. If not, it will try the chip next door, and if that's busy, then it will try any of the POWER7 chips in the machine. So in this case, we can't predict which cores are going to be free and which allocated until runtime. We actually go over our 0.4. So here we've got a pretty bad example. This half a CPU is on the same chip, so that's not too bad. That's still local memory. This one is on the next chip in the machine, but this one's a long way away. It's the furthest chip you can imagine across the machine. If it's a big machine, it actually could be in a different CPU book or a KEK. Now this means there's a secondary effect in here. Because we've got VP of 4, this will be quite quick because it's got local access to the memory. This will be going quite a long way across the machine using the XYZ bus perhaps, and this will be using the AB bus, which can take a lot longer to get hold of the memory. But you'll notice in this case in here, 3/4 of the memory will actually be more remote than the local memory of our actual POWER7 core. And it depends on the application whether that memory access is actually going to hurt our performance. But a lot of it is actually going to have to be remote now, where we try to avoid that in most circumstances. And let's say the whole machine gets very busy, we've guaranteed only 0.4. This number should be what we'd hope would successfully run the workload. And we're competing with the CPU cycles in the pool with all the other logical partitions, and so if it's very busy we could be forced down to just our entitlement, plus a little bit perhaps based on our weight. But if it's very busy we may only get 0.5 or 0.6. It's no wonder that this configuration doesn't work very well on a very busy machine when this particular workload is high. So then I asked Jane, well, what sort of physical CPU time is this virtual machine actually getting? And the answer is, well, 1.2 at the moment, but we're not working very well because there's very little spare capacity on the machine. So we're actually starving this logical partition from CPU resources, and we're spreading it across the machine unnecessarily. So I recommended that we increase the entitlement to cover this demand to 1.5. It could be needing 1.5 or even more to actually get through the peaks, but we can't really tell. While it has such a low priority, it may not be getting half as much of what it actually needs. They made those changes to Jane's machine, and there was a sudden dramatic leap in performance. Now, instead of struggling to 1.2 CPUs, it's guaranteed to have that available at all times. And this means that there's much more responsive, and there are now 0 user problems. Then they asked me, what's the next stage of tuning should we actually do? And I said, let's reduce the virtual processor number. And yes, I am serious, reducing the virtual processor number for higher performance. Unfortunately, the customer didn't go ahead with that because they couldn't cope with it psychologically. So here we have the entitlement of 1.5, which covers the normal use so that it's guaranteed it doesn't have to struggle. If we actually reduce the VP to 2, then the chances are when we start up this logical partition, it will allocate 0.75 onto 2 cores on the same chip with local memory. We still have a headroom of 33%. We could go up to using the whole of this core quite comfortably, taking in our peaks, but we have 100% now local memory. This should give us a further performance boost. Here we go, email from Rod now, looking at nmon on the top processor data, and it was an urgent plea. Please, I need to know, why is Oracle showing 95% of memory use? I don't understand. He was saying that the Oracle SGA and PGA is not greater than 10 gigabytes, and the total RAM is 32 gigabytes. Looks over here, we have the Oracle process in here, and it's using 95 out of 100. Oh no, how can it possibly do that? Well, Rod's having a bad day. This is 95 megabytes of memory being used by the Oracle process. The actual SGA isn't reported as part of the process. It's seen as a shared memory segment which is independent and probably loaded into lots of different processes. So, just having a bad day. Fortunately, he asked the question in a polite way. A lot of people tell me, why has nmon gone wrong? Even when it's down to them actually not understanding the data they're looking at. So, a nice easy one. Just tell Rod, you're overworked, go and have a rest, and read more carefully when you're looking at the data. Email 4 is from Sally. She's been looking at the processes in particular and decided that she's discovered a memory leak. And first I'd like to say that memory leaks are fairly rare. It's easy to convince yourself you have one when you don't. Modern computer languages have this as a known problem area, and there's plenty of libraries and tools and infrastructure to help developers find memory leaks and fix them before they release code as part of their test cycle. Now, Sally says she's been monitoring the processes. When they're busy, they grow in size, that's expected, but later on, when they're idle, they don't get smaller. Obviously, they're leaking memory. Normally, this is not true, and I hope to explain it in the next file or two. So what's happening here? Well, when we start off, we start with a fairly small amount of memory, just the bare minimum to get it going. When the processors get busy, they do use this malloc system call to grow their virtual memory size to give them extra scratch pad areas, places to load files and manipulate data. Now when the process goes idle, it uses this free library call, but that doesn't actually free up the memory from the process. It just releases the memory into what's called the heap, and it keeps a list of all the free memory pages that were used but now are not used. When you make further malloc calls, they actually use that free space from the heap first. Only if the heap goes to a very small size does it actually then make a malloc call to actually get more memory pages. Now if you're genuinely not used for a long time, then the operating system detects that you haven't used these pages, typically in the heap, for a long time, and it will actually page those out onto the disk, so you're no longer actually sitting this virtual memory in memory. So what we should be looking at is, for these processes, is this resident set size. This is the amount of memory is actually occupied by the process, and also note that it only gets paged out if memory is in short supply. If there is free memory inside the logical partition, then it won't bother paging things out because it may be useful to have it in memory in the future. I tend to find that 99% of the time when people think they have a memory leak, they don't really. So here's email from Bob. If you remember Jane, she had one vital logical partition that was running far too slowly, grinding to a halt, and it turns out she was giving the resources that this one needed to the other logical partitions. Quite often we have to look at the whole machine now and what's going on, rather than just one LPAR in isolation. So Bob wants us to do a review of the whole machine, all the settings and what we can recommend. And then we tend to get the details in many bizarre formats. So spreadsheets are quite nice. Sometimes they're handwritten notes and documents, and we ask how current is this, and they say, well, this is what we set up 6 months ago, but we have actually added 12 different LPARs, and we've made some changes to some other ones, and I don't have the details, and you're starting to worry now. We've actually had people do screen grabs from the HMC with the settings for logical partitions in it. One person actually was going to send us pictures of the HMC screens, and it really worries me when people say things like that. What would I actually recommend for the best tools? We've already mentioned the HMC scanner. Very cool, very quick, and gives us a nice spreadsheet so we can do some calculations on the numbers nicely laid out. Sometimes we have these handmade reports and we have to worry about the accuracy. Some people are running HMC commands remotely and pulling out the data, so we get the output from a whole bunch of different commands. Often there's something missing in there, we have to ask for an extra things, and usually they're happy to change the commands to get the extra data. If you have system plans from your HMC, they can be used. Typically you end up with a large PDF document, and if you've got hundreds of LPARs, it can be a bit of a pain looking through all of those and all the profiles to actually build up a spreadsheet that we actually like to look at. Now normally I work on bigger machines and they're using bigger LPARs, but I'm now seeing lots of quite large machines running micropartitions, LPARs with less than one CPU allocated to them, or smaller numbers. Maybe a micropartition would include 2, 3 and 4 CPUs. And I've had to rethink what I'd recommend for these small and micro partition setup. I see again and again a common E equals 0.2 and VP equals 2. This is going from the minimum amount of entitlement to the maximum number of VP. We've already discussed that. Ghastly way of doing things, but common. Now I do understand the pressure. You have loads and loads of logical partitions, but a physical number of CPUs you need to run it on, and you have to divide those physical resources into all the logical partitions you want to run. And if we look at the virtual processor number, it very much sounds like it's free. We asked People may ask, what's the difference between 3 and 4, and how much extra does that cost? Well, it doesn't seem to cost you anything at all, does it? So people like to be generous and allocate lots of virtual processors because they don't seem to be a cost to them. And of course, if you have very high capacity in your logical partitions, then there's no need to monitor them. They can always grab whatever they need. And I think this is pretty bad thinking. What we end up with is the total virtual processors can be up to 10 times the physical CPU cores. They're the rules that limit us. But I have seen machines, big 64-way machines, that are running 300 or 400 virtual processors on them. And then we're actually cutting our physical cores into lots of tiny little bits. And this really does have some bad side effects that we want to explore now. Just because IBM says you can do this doesn't make it a good idea to do everywhere and every time. But my customers then say, but IBM promised overcommit was okay. And it is true, it is okay. But I'd like to give you an analogy. It's also okay to overcommit your disk space if you have thin provisioning technology. Works fine, provided all the users don't demand their maximum disk space. If they do, it's a complete and utter nightmare. In the case of disk space, you have to return disk errors once you got your disk provisioning pool down to 0. In the case of our CPUs, it's not that bad. If we have lots of LPARs demanding their maximum VP, they have to fight for resources. They'll get all the resources that are available. It may not be as much as you are hoping that they would all get because we've overcommitted our resources. They'll all get cut down using some of our techniques like weighting factors to work out who gets what. Only the entitlement is guaranteed, and there are also effects in memory affinity that can hurt us too. Let's look at these visually. Here we got low entitlement but high virtual processor numbers. Now this is good for flexibility, if we get as many LPARs as we can onto a particular machine. But we can get into this LPAR shredding, as I call it, causing unnecessary CPU cache misses and memory bus transfers. If we look at one CPU here, it is running 10 different logical partitions. When this guy runs, he gets his stuff into the cache. 9 guys knock his stuff out of the cache before he gets to run again. Low cache hits. Memory transfers. If we look at this guy in here, he's got memory, but it's spread across the entire machine. Big opportunity for having to do lots of memory bus transfers pointlessly. Here are the same number of logical partitions, and I put them into what I call clumpy mode. Let's make the entitlement about right for the normal peaks, and then get the VP correct just a little bit higher to give us a comfort factor in here. Now we find that this logical partition in here is only competing with 2 others on this particular CPU, and it has 100% local memory. Much better affinity. Look at these 2 examples in here. Which set of LPARs do you think's more efficient? This guy's got dedicated caches in the CPU, dedicated memory, local transfers. These guys maybe unnecessary memory transfers across the machine and competing for clock cycles and level 3 cache. It's obvious when you look at it in a diagram like this. The memory subsystems in our POWER7 7 Plus servers are really good in terms of their multiple gigabytes per second transfer rates from the, I think, 68 from a single memory controller to across the machine, which is running at 40 to 50 gigabytes a second. But there are a limit on the number of transfers that can happen at any one time. If you look at your red books and look for those diagrams that shows the interconnection between all the chips, the X, Y, Z and the A, B buses, then you'll see how many can be concurrently active doing a transfer at one time. If you're shredding your LPARs across the machine, you're greatly increasing the chances of having to do remote memory accesses and hammering those memory subsystems. Now you'll notice on this diagram in here, there's no units and there's no numbers, so I'm not going to give you a hard numbers for these things, But if you unnecessarily shred your logical partitions, you're drastically increasing the chances of getting into a thrashing situation in your memory subsystem compared to clumpy LPARs where you've localized them and stopping these remote memory transfers. We've seen this first, though, in our very biggest machines, the 795, but only in the small configurations of that machine. If you only have 2 or 3 of the CPU books, the number of connections between them is quite low. Because when you go and add extra books, the number of connections goes up as an exponential graph, and then we can actually handle the memory transfers. This is why on the very small configs you can only have 32 or 24 CPUs in individual logical partitions, so it can be localized onto a book. For Jane and Bob's questions, let's revisit that entitlement to virtual processor ratio. In the good old days, when we had dedicated machines or dedicated CPU LPARs, we tend to use this 80-20 rule or something similar. We work out how many CPUs we typically need to use on a daily basis, and then we add a contingency to handle those exceptional peaks. This is sort of well known and well understood. If we're using shared CPUs but they're capped, again we've got a hard limit, and we should be using the entitlement to cover the bulk of the daily work, and then we have a little bit of contingency in here, and then the capped level so that it can't step over the top of that. When we get a shared and uncapped, all too often we get something like this. We actually reduce the entitlement to much lower than it really needs to run, and then we put a great big VP number in here to actually make up the difference, so we're back up to the 100%. It's almost the exact opposite to like a 2080 rule. I'm not quite sure why we're tending to do that as default. I know the overcommitment problem is we don't have enough physical CPUs to allocate what they need to actually run. We're just hoping, maybe it's praying, that the vast bulk of these LPARs won't actually do anything today. In actual fact, we're doing something far worse when we go for a VP of 10 times the entitlement. We've already said that VPs feel like they're free, they're not a cost item, are they? It feels safer to have them up higher. It means we don't have to do any monitoring because they'll just take the CPU they need. But there's quite a high cost for these high VPs, and it's only sort of recently we understood the cost of doing that. IBM, I think, didn't really expect users to go for this extreme E to VP ratios, and we also then, if we add it up for the entire box, we have this virtual processor to physical processor ratios, and I've seen values of 400%. If all the LPARs want to use all their VPs, we actually got a machine that is 1/4 of the size to run that. That's quite a high risk way of running your machine. Of course, you can go up to 1000% in your VP to PP ratio, and we really have to worry about those configurations. So I started looking at some sort of rule of thumb. So these small shared uncapped LPARs, how to sensibly go about this. Well, we need to make that entitlement, as we say it down here at the bottom, that covers our regular peaks that we're going to guarantee is available to the LPAR. Don't just make this a very small number, we actually have to go on and monitor what's going on. Then we're going to set the VP ratio to a bit larger. We were using 80-20 rules. Here we're saying 25 to 50% extra, particularly in these micro partitions and the small ones. So if we got the minimum entitlement up to 0.6 of a CPU, then the VP should be 1, and we've got no real choice in here because we can't go to less than the whole CPU. And we have a sort of headroom percentage like this. Then from 0.7 to 1.4, 1.5 to 2.3, and up we go. Now you may make some adjustments to this to cater for what you want, but this is a much lower VP numbers than I've seen in practice. I've seen these guys being up at the 4s and the 5s, and that's where we're spreading things out far too much. Now I'm not alone in pointing out these things. Other people are doing this. Steve Nasipany and Rosa Davidson, for example, have talked about these at conferences and the virtual user group meetings. Perhaps this is the first time it's been put into a movie. It's highlighting though that we need whole machine configuration documents sorted out, and the HMC scanner seems like a low-hanging fruit way of doing that to me, and whole machine monitoring so we can set these entitlements and their matching VPs to sensible numbers rather than wild guesses months in advance. Perhaps whole machine monitoring is another movie though, it's a large subject. There are some good places to go for some extra information in the Red Books. The Performance Guide, particularly good. It actually has there in Chapter 6 a diagram, like we've been exploring in this movie. They call it not optimized and optimal rather than shredded and clumpy. Perhaps a more formal way of documenting it. There's also the POWER7 7 Plus Optimization and Tuning Guide, written by the true guru level people, and lots of advanced content in there. Definitely worth going and have a look at that rapidly growing Red Book. Email 6 then is from Sue, asking about sizing hints and tips when using rPerfs to decide a config for a new machine, perhaps doing consolidation of older machines, for example. Well, the good news is there's a recent article in the IBM Systems magazine. The URL is here, AX Tips, Techniques, Migration, rPerf Metric. And it goes through in a nice article describing how to do that. We've been doing this for 15 years or something now. No rocket science in here, but very briefly. We look at the older machines and their rPerf ratings. And we'd have to scale those if they're using logical partitions. Perhaps they're only using half of the machine. And so we scale it down to the size of the LPAR. Then we need to look at the utilization for the LPAR, so that if it's only using 50% of the CPUs that it has, then we can scale down the actual requirements there. Then we're going to do a quick guesstimate for new workloads, and then we might know that perhaps the website is growing 50% every year, so we add in a growth estimate of the CPU requirements there. And that's how much we actually need to run it. We then might use the 80-20 rule to say, well, we'll put in a little bit of comfort factor in here so we can handle peaks during the year and during busy periods. Once then we have that aggregated rPerf value, we can then start doing the configuration side of things, find a suitable machine. Perhaps we need 500 rPerfs, and we can find a machine that will do that. Perhaps we say, well, hang on, none of our LPARs are very big, so we could actually use 2 smaller machines to reduce the price of it. Then we'd have to do sensible things like what gigahertz rating and how many CPUs we need, and laying out the memory inside the box. Once we've done that, then we have our configurations and we can ask for a price, and off we go. But, there's a big but there. There are a number of assumptions being made here about rPerfs, and these can really badly catch you out. So here are my 10 golden rules, or how to avoid performance mess-ups by assuming too much. Firstly, we need highly threaded workloads. If you have 10 CPUs, SMT4, you've got to have 40 concurrent threads, otherwise you're not going to use the full power of the CPUs. In fact, those threads may instantaneously in the next fraction of a second try and do some disk I/O or network I/O and stop. So you have to have another set of threads to actually then kick over to and keep the CPUs busy. So you need several times that number of workloads, threads, to actually keep the CPUs busy. The machines need to be well tuned, not out of the box settings. 2 years ago the out of the box settings were put, improvements were put into those, but we still have things like jumbo frames are sort of mandatory if you want your networks to fly, and queue depths and things for your disks. We need some of those things tuned up. Number 3 is full spec RAM. When we do an rPerf test, of course we're going to use the best configuration we can think of, which means all the memory slots are used, and lots of memory, generous amounts of memory, because that optimizes things and keeps the disk I/O down. So we're going to have to use a similar configuration. If you've got unused memory slots, then you're not going to get the rPerf value you were expecting. And the same with keeping the memory large and fairly even in sizes of your DIMMs. We're going to have no disk issues and no network issues. If we're moving up from an older machine that is actually disk bound or network bound, we'll bring that to the POWER7 machine. It's not going to go any faster. It's still going to be network or disk bound. And so we have to have those things fixed, otherwise the POWER7 7 Plus processors will just get to waiting for the slow disks or slow networks even quicker and wait just as long. Also, when we do an rPerf rating for a particular machine, we use the current applications, the current database, middleware, web servers that are available at that time. If we're taking it from a box that's 5 years old, it's going to have old versions of these things, and so they will not be optimized over those 5 years, and we're not going to get the benefits. In fact, some of the database, for examples, have specific fixes for POWER7. And if you haven't got an up-to-date version of that database, you're not going to get the rPerf value you might be expecting. Now, when we run benchmarks, number 7 here, we use the latest version of AIX with the latest service packs. These service packs have a number of things in here. They have some bug fixes in here, which are good to have. We're going to have some security fixes in here, which are good to have. But they also have performance tuning impact, and we need those to make sure we get the best performance. Again, if we're using a 3 or 4 year old copy of AIX, it's not going to have the benefits, and we're not going to get the rPerf value you might be expecting. Also, when we do rPerfs, we do them with large LPARs. On the smaller machines, typically they have one LPAR for the entire box. On some of the bigger machines, maybe they have a small handful of logical partitions. The further you get away from the official rPerf number with its official number of CPUs, the more assumptions you're going to make. Particularly when you go below one CPU or micropartition, and particularly if the entitlement is wrong and the VP is too high. By the time you get into 2, 3, 4 CPUs, or approaching the actual quoted rPerf number for perhaps 8 CPUs or whatever it is for this particular machine, then you're in safe territory. Number 9 is current firmware. The firmware development team have done an excellent job with the newer machines, and the newer levels of firmware have great features in them that improve the layout of LPARs and the raw performance of the machine, and the latest firmwares have things like DPO to automatically move the LPARs around inside the machine to increase the performance. If we haven't got the current firmware in the machine, then we're not only exposed to some problems that have been removed with that firmware, but we're not going to get the performance you might be expecting. Also, it must be bug-free. We do have some bugs in our machines and our software, and I do get very frustrated when customers say, well, this box isn't as fast as you promised us, and we say, okay, let's change some of the things in the above list, like updating AIX and updating the firmware. They say, no, we've got to fix their performance problems without changing anything, with zero downtime. The only thing we can use in this sort of case is magic pixie dust. Now, I do appreciate in real life, in real production machines, in a real computer room, you can't have this perfect world with brand new everything and perfect everything. If you're failing on one or two of these things, maybe just a little bit, maybe the AIX level is one level back, or the firmware is one behind, then you may well do quite well. But if you're failing on a whole bunch of these, or the AIX level and the database is from years ago, then you're quite unlikely to hit the rPerf values you might be expecting. But do contact us. You pay for IBM support, and we are there to support you and work through the problems. Although you do have to let us upgrade and fix things if you want the performance. Email 7 is from John. He's asking, is my box full, busy or not? Let's have a look at a worked example of this finding the spare capacity. In POWER7 machines, then we tend to spread all the LPARs and the work across lots of cores for maximum performance. In this little example, we have 8 cores across the top in here, running multiple logical partitions. We put an X there for just one busy program running. We have 32 VPs in here if we add up all the logical partitions, and only 8 cores. So VP to PP is 4 times overcommit, or 400%. The question is, all these cores are actually look like they're busy, and they'll be marked up as that. Can we cope with a peak in demand, and can we actually start a few more logical partitions on this machine? If we dig into some of the details, we've got uncapped high virtual processor logical partitions in here, but just a few busy threads per virtual machine. All the physical CPUs will rapidly get used up. If we run the AX command LPAR stat and look at this APP column, this stands for Available Physical Processors. It's a bit of an odd number here because if we switch it on and make it available so that the LPAR can collect this stats, then it is actually a machine level value. It's telling you how many physical processors there are in the entire shared CPU pool. In our little case in here, it will say 0, none. They've all been accessed and used concurrently in the logical partitions, and it looks like the machine is 100% busy. But if we log on to each individual virtual machine, we can see that there's plenty of second, third and fourth SMT threads available. And I typically get asked, you promised that I could run 3 more virtual machines in here, this is no good at all. Or can I measure that spare capacity in my machine and find out if I can run more workloads or more virtual machines? The answer is it's tricky. I'll give you an analogy. If my car uses all 4 cylinders driving to the local shops, how fast can I go down the autobahn? And the answer is, it's almost impossible to tell without putting your foot down on a nice straight road and working that out. Power systems are optimized for maximum performance, making good use of all the resources in the machine, not for minimum hardware use. If we could switch on a minimum hardware use, then we could squeeze all the LPARs down to one end of the machine, and whatever's left would be the spare capacity. But of course we haven't got a mode like that because it would be wasting a lot of resources. We end up with lots of islands of overlapping spare capacity in the machine, and it's very difficult to have a statistics that can work all that out for you. If you have lots or hundreds of virtual machines or logical partitions, this gets increasingly harder to work out. So we're going to give you 3 approaches, and the first one is we'll do a review of all our virtual machines as we looked at earlier on. Raise the entitlement to cover the basic usage every day for efficiency reasons. Lower the virtual processor number so we can force higher SMT thread use. Then we're going to monitor the CPU pool, and we should then be able to detect with the LPAR stat and the APP column of the unused CPUs inside the machine. Now the downside of this is that it's quite manpower intensive. If you have 200 logical partitions, this is going to take quite a lot of time, and it takes a lot of virtual machine changes adjusting those entitlements and virtual processor numbers. Approach 2 tries to be a bit more pragmatic, so we do the same as we did in approach 1 for the larger, the important, the vital virtual machines. Then for the rest of them, we just try to squeeze them all. We're going to use a standard rule of thumb. Perhaps something like the virtual processor number should be the entitlement plus 1 rounded. If we're looking at it in a spreadsheet, we could actually type that in. Then we're going to monitor what happens, and we're going to wait for some complaints. Because we used a rule of thumb, we may have actually squeezed some of those smaller logical partitions too much, and then we'll have to adjust them back if we get complaints from the users. Approach 3 is quite sneaky, and I'm quite proud of this one. We're first going to fix a few of those virtual machines as we have before. Then we're going to remove 1 CPU from the pool each day until it really starts to hurt. We can park a CPU, remove it from the pool, by putting a CPU into a dedicated CPU LPAR. This means it's no longer available to the pool. As long as the dedicated LPAR is running, it doesn't actually have to be doing anything at all. It can be at the SMS menu, that's good enough to lock out that CPU. Then we wait until the performance dips. Now, depending on how big the machine is, on how long this will take, taking 1 out a day, or the complaints start arising about the performance. When we hit that point, we can then use dynamic LPAR to move a CPU back from the dedicated LPAR back into the pool and get out of the problems with performance dip and a complaint. Those parked CPUs in this dedicated CPU LPAR clearly identify then spare capacity. These are not being used at the moment, and these are available for hitting peaks in workloads and for starting new logical partitions. Well, I'll leave you with this little summary of what we looked at with our 7 emails, and do watch out for those ratios: entitlement to virtual processors and the total number of virtual processors in the LPARs to the physical CPUs in the pool.